Welcome to NovaSleep. Tonight we are not looking out at the stars, but inward, into the vast hidden cosmos of your own brain. Every thought, every memory, every dream is a signal flickering in the dark, and together they create the story of who you are. But this story is stranger than you imagine. In the next moments, you will hear 80 discoveries about the mind that reveal how memory bends, how the brain edits reality, and how the quiet work of sleep shapes the person you become. Let each one carry you deeper, until curiosity slowly gives way to calm, and you drift with your own thoughts into rest. By the way, if you like and subscribe to my video, this is the most effective way to support me. If you can tell me where in the world you are watching from and what time it is, I would love to read it in the comments. 1. Memory rebuilds itself every time. Memory does not sit in the brain like a film on a shelf. It lives as a pattern spread across many regions and wakes when that pattern is reassembled. Each act of recall unlocks a flexible state in which the memory can be strengthened, reshaped, or even weakened. The brain treats the recalled event as fresh material, mixing it with the current mood, the present surroundings, and any new facts that have arrived since the event first happened. What returns to storage is similar, yet never exactly the same. This rebuilding depends on networks that bind together pieces of sight, sound, place, time, and feeling. When those networks reignite, proteins must be rebuilt to restabilize synapses. If that rebuilding falters, the trace may fade or bend. This explains why two people remember a shared scene differently, and why details shift over years. The design is not a flaw, it is a feature that lets knowledge stay alive in a changing world. A living memory can be edited without noticing. A new explanation slips into the story. A later photograph becomes fused with the original scene. A rumor nudges the color of a feeling. The change feels natural because the brain seeks coherence. Once rewritten, the fresh version feels authentic, which is why confidence is a poor measure of truth. The same machinery that shields identity also leaves it open to drift. This plasticity carries a quiet power. Therapy that revisits a painful event can graft in safety signals so the memory loses its bite. Studying that deliberately returns to a concept while adding a new angle allows understanding to grow richer. Habits can be re-encoded when the old trigger is recalled and a different action is rehearsed. The past is never fixed in one piece. The past is an active conversation the brain keeps having with the present. 2. Adult brains can grow new neurons. For a long time, the adult brain was treated as finished. Evidence from animals and humans now shows new neurons appear in specific places, especially in a part of the hippocampus involved in pattern separation. These newborn cells are not decorations. They are flexible recruits that can help reduce interference between similar memories, which becomes essential when days blur and places repeat. Even small additions can shift how cleanly two experiences remain apart. New neuron birth responds to life. Aerobic movement, rich learning, and environments loaded with novelty raise the rate. Chronic stress and persistent inflammation push it down. Nutrition, sleep quality, and social connection also matter. The effect is modest yet meaningful, and it interacts with many other forms of plasticity that remodel synapses and circuits. Growth of new cells joins a wider orchestra of change rather than acting alone. These cells mature in waves. At first they are excitable and eager, then they settle and contribute to stable networks. That timeline means timing can matter. Training that arrives when cells are most ready can be captured more easily, leading to memories that separate cleanly instead of smearing together. It also means droughts of novelty can leave circuits crowded with echoes that compete for recall. The larger message is hopeful. While decline can happen, the adult brain is not a closed box. It remains a living organ that reshapes itself in response to what a person does and feels. Layer by layer, new cells and fresh synapses can help preserve clarity in a world that keeps repeating patterns. The door to change never fully locks. 3. The hippocampus stitches moments into time. Episodic memory depends on more than places. The hippocampus also tracks sequences, building the timeline that turns scattered moments into a story. Inside it, live cells that fire at particular steps within an experience. As a task unfolds, different cells light up in order, forming a quiet ruler for the passage from beginning to middle to end. The result is a thread that ties what happened first to what followed next. This stitching helps separate today from yesterday, when both happened in the same room with the same people. Without it, events would pile up without order. The brain would find the right scene yet lose the sense of when it occurred. A working sense of time emerges as chains of neural activity that sweep forward, sometimes faster or slower depending on attention and emotion. A tense moment stretches, a routine commute collapses. Sequences let the future be rehearsed. When planning a route or a conversation, the hippocampus can run short previews that feel like imagination. Those previews use the same machinery that records what actually happens. Memory and foresight become twins born from one process. The better the stitching, the easier it is to simulate outcomes and avoid mistakes before they start. Time threads can weaken under stress or injury. When the chain loosens, events feel scattered, and decisions become harder because cause and effect blur. Strengthening the thread means creating experiences with cleaner beginnings and endings and letting them consolidate during sleep. The hippocampus then has clearer fabric to weave, and the next day feels more navigable. 4. Dreams weld fragile memories into strength. Sleep does more than refuel the body. It changes the fate of what was learned. During deep stages, the cortex falls into slow waves while brief bursts called spindles pass over like trains. Hidden inside are replays of waking activity that compress the day into fast summaries. The hippocampus pushes out patterns, and the cortex receives them, turning shaky traces into durable structures that require less help to survive. Later stages add a different service. Rapid eye movement is a theatre where emotion and imagery mix freely. Here, the brain integrates what matters with what already exists, testing combinations that would be too distracting while awake. Emotional charge can be reduced without losing knowledge. Creative associations appear, knitting distant facts into a network that answers better when needed. The welding is selective. The brain does not save everything. It saves what carried prediction errors, meaning events that surprise the internal model. It saves what will help tomorrow by strengthening the connections that lead from cues to useful actions. Noise gets trimmed away. The result is not a perfect archive. It is a tuned instrument built for the next performance. Disruptions show how important this is. Short nights, fractured rhythms, and light late in the evening can blunt replay and spindles, leaving learning brittle. Fixing one night cannot fully replace a string of regular ones. A steady rhythm builds a steady memory landscape. Dreams then become a workshop that keeps working long after the day has ended. 5. Smell can unlock a forgotten decade. Odor pathways reach deep into limbic regions without the relay that most senses pass through. That shortcut gives scent unusual power over memory. A faint trace of an old perfume or the air of a childhood kitchen can pull up scenes with uncanny detail. The images feel more present, the emotions more immediate, because the circuits that tag salience and value are engaged from the first breath. This effect is not only about intensity. Smell is tied to context. The brain encodes odors together with locations, seasons, and social scenes, so a single note hits many keys at once. When an odor matches the original context, retrieval gets a boost known as context reinstatement. Words and pictures rarely reproduce that exact context, which is why they feel weaker than the right scent. The pathway can aid therapy and learning. Reintroducing a neutral odor during study and again during sleep can stabilize what was learned, because the brain treats the repeated cue as a link between states. In emotional work, carefully paired calming odors can help soften harsh associations. Care is needed, since powerful odors can also fuse with negative scenes if misused. Age, illness, and stress can dull smell, and with it a subtle route to memory health. Protecting this sense protects access to a well of autobiographical detail. It is a reminder that memory is not just in the head as an idea. Memory is multi-sensory information woven through the body, and scent is one of its deepest threads. 6. Stress can shrink the memory center. The hippocampus is sensitive to stress chemistry. Short bursts of arousal can sharpen learning by marking events as important. Long floods do the opposite. Elevated stress hormones over weeks push dendrites to retract and reduce the birth of new cells. The result is a smaller, less flexible network that struggles to separate similar experiences. Life begins to feel like a repeating loop because traces overlap. This shrinkage is not destiny. Remove the pressure and the tissue can regrow to a degree. Exercise, social support, and structured novelty help rebuild branches. Sleep also helps, since it lowers baseline stress chemistry and promotes replay that rewires synapses. The timeline of recovery is measured in weeks and months, not hours, which can make early gains easy to miss. Patience matters as much as technique. Stress also biases what is remembered. The brain favours threat cues and neglects context, which explains why a harmless sound can feel linked to danger and why neutral details vanish. The amygdala pushes its priorities, and the hippocampus under pressure cannot fully anchor them to time and place. Later, when the chemistry eases, the world can appear flat because safe scenes were never stored well. Balancing the system means more than reducing stress. It means restoring contrast. Deliberate periods of calm, rhythmic breathing and predictable routines give the hippocampus time to sort the day. Small wins that signal progress help reset valuation. When the load lightens, the memory center begins to branch again, and learning regains its depth. 7. A doorway can reset short-term memory. Walking from one room into another often wipes the reason for the trip. This is not simple distraction. The brain segments experience into events, and boundaries like doorways tell it a new event has begun. When a boundary is crossed, the temporary buffer that held the last goal is cleared to make room for new predictions. The system trades perfect recall for speed, which usually helps more than it hurts. Event segmentation is useful in complex environments. It keeps the present flexible by preventing old goals from clinging too long. The cost appears when a goal spans a boundary. Without an active cue, the plan evaporates. Returning to the original room often restores it because the prior context wakes the old event model. Context is not decoration. Context is part of the memory itself. Design can work with this feature. Grouping related actions in one place reduces boundary losses. Visual anchors that travel across rooms keep the brain from declaring a new event too soon. Clear starts and finishes reduce the chance that midstream intentions dissolve. The same logic explains why switching apps repeatedly makes details slip. Digital doorways count as boundaries too. This everyday quirk reveals a deeper rule. Memory is packaged along with the scene that held it. The mind remembers what to do by remembering where it is. Spaces tell stories and the brain listens. When the story changes, short-term memory obeys the new chapter and lets the last one go. 8. Memories shift location as they mature. Right after learning, the hippocampus carries a heavy load. It binds together the scattered features of a new episode so that one cue can call up the whole scene. Over days and weeks, responsibility moves. Patterns become embedded in the cortex, which handles them more efficiently and with less need for the original index. The memory becomes easier to access, though some detail can blur. This process depends on replay during sleep and quiet rest. The hippocampus repeatedly drives the cortex with compressed versions of the experience. Over time, the cortex learns the structure and can answer directly. The memory is still shaped by the model already present in those regions, which means it can bend toward what was expected. That bending can be helpful when generalization is needed. Old memories are not frozen. When a consolidated memory is recalled, it can return to a flexible state and be updated before it is stored again. That update can insert corrections or distortions. Systems consolidation is therefore not a one-way transfer. It is a conversation between fast binding and slow structure learning that continues across a lifetime. This explains why people can keep the gist of an event for decades while losing fine detail. It also explains why well-learned skills feel effortless. The cortex has absorbed the pattern. The hippocampus is freed for what it does best, capturing what is new and stitching it into the timeline. 9. The brain stores maps of places inside. Navigation relies on cells that mark location, direction, and distance. Place cells become active in specific spots, grid cells fire in repeating patterns that form an internal lattice, and head direction cells signal which way the head points. Together they create a dynamic map that updates as the body moves. The map is not a picture. It is a code that guides action moment by moment. These maps do more than guide walking. They help organize memories by anchoring events to where they occurred. A scene remembered later often brings back the route taken to reach it. The overlap between navigation and memory is not an accident. The hippocampus and nearby areas serve both, turning space into a scaffold for the stories of life. The same machinery can map abstract spaces. People navigate social swirls, ideas, and sounds using relative distance in a mental space. Cells that once fired for corners of a room can fire for dimensions of a concept. This reuse gives the brain a common language for many kinds of travel, which may be why spatial strategies like memory palaces work so well. Damage to these systems brings a special confusion. The streets of a familiar neighborhood feel wrong. New places refuse to stick. training can help other cues take over, yet the easy grace of moving through the world is hard to replace. The internal compass is one of the quiet wonders the brain builds without instruction. 10. There are neurons that mark time. Within the hippocampus and the related circuits live neurons that activate at particular delays during a task. They do not care about where the body is, only where the mind is within a sequence. One cell might fire near the start, another at the midpoint, another near the end. Together they create a scaffold that tells the rest of the brain how far an event has progressed, even when nothing visible changes. These time markers help keep order when events look alike. Two similar actions can be stored as different because they happened at different steps in a sequence. The markers also let the brain predict what should come next. When the expected step fails to appear, the prediction error flags the moment as important and learning rises. Time coding and learning are partners. Perceived time stretches and compresses as attention and emotion change the density of these patterns. A novel moment lays down a thick code which later reads as a longer interval. Routine compresses into a thin code that collapses in memory. Fear and awe alter pacing, which is why crisis and wonder feel elongated. The experience of time is not a clock on the wall, it is the shape of neural activity. When time coding falters, the world loses sequence. Tasks become harder because steps blur together. Narratives lose clarity and predictions misfire. Repair begins with rhythm. Sleep strengthens the sequence code and steady daily cycles restore anchors. With structure back in place, the brain can once again measure the path from now to later with quiet accuracy. 11. Sleeping brains replay the day in hidden bursts. During rest, the hippocampus does not stay silent. It compresses long episodes into brief flashes of activity, replaying patterns at many times the waking speed. These replays look like rehearsals, sending out condensed versions of the day's events to the cortex. Such bursts often happen during quiet, non-REM sleep and even during short pauses while awake. Each replay strengthens connections and helps shift fragile experiences into long-term storage. The bursts are not random. They often occur in the same order the events originally unfolded, almost like a miniature film sped up. Experiments with rodents have shown place cells reactivate in the sequence of a maze they just ran. In humans, memory traces for new words, faces, or tasks show similar bursts detectable with scalp electrodes. Replay is a silent teacher that keeps working when the mind is unaware. These hidden rehearsals appear especially after novelty. The brain chooses which patterns to replay by weighing surprise, relevance, and emotional load. An unusual conversation or a stressful encounter is more likely to be replayed than an ordinary routine. This bias means sleep is not passive rest but active editing, selecting what will survive and what will fade. If replay is disrupted, learning suffers. Disturbed sleep, constant interruptions, or strong stimulants can cut off the bursts before they finish. The next day, the memory feels weaker and harder to call up. Protecting deep streams of sleep protects the invisible theatre of replay, and with it, the strength of what was learned. 12. Slow waves and spindles act as memory couriers. As the brain enters deep sleep, vast populations of neurons fall into slow synchronized oscillations. Riding on top of these waves are faster ripples called spindles, sharp bursts that look like short trains on an EEG. The timing of slow waves and spindles is crucial. The slow wave opens a window, the spindle carries the package, and hippocampal ripples deliver compressed memory traces. This coordination allows communication between brain regions. The hippocampus offloads patterns, while cortical areas receive and integrate them. Without the slow wave to open the gate, spindles cannot deliver effectively. Without spindles, the ripples lack a courier. Together, they create a relay that converts a labile trace into a durable cortical pattern. Studies show that the number and quality of spindles predict how much people remember the next day. Enhancing spindles through auditory tones played at the right phase can sometimes boost retention. Conversely, disrupted spindles reduce learning even if total sleep time remains the same. Quality of rhythm matters more than sheer quantity of hours. This deep choreography illustrates why sleep feels restorative. It is not merely the absence of wakefulness, it is an active system that times pulses of activity with exquisite precision. Every night the brain engages in this hidden postal service, sorting and delivering the day's information into lasting networks. 13. The brain can learn while asleep in small ways. For decades, the idea of sleep learning was dismissed as pseudoscience. More recent work shows that while full concepts cannot be absorbed, certain associations can be strengthened. Pairing tones with mild odours or emotional cues during slow-wave sleep alters later recall and preference. The brain is not listening in the usual sense, but is still able to integrate simple links. The effectiveness depends on timing. Deep non-REM stages seem most sensitive to associative conditioning. When cues arrive during REM, the effect is weaker or absent. The brain cycles between receptivity and protection, balancing the need to shield memory consolidation with the occasional need to update it with cues from the environment. This limited capacity is not trivial. It suggests that memory networks remain plastic even while unconscious. Odor cues paired with foreign vocabulary learned in the day can improve later test scores if replayed during sleep. Safety associations paired with soothing cues can reduce the bite of fearful memories. The system is narrow but powerful when targeted with precision. Sleep learning is not a shortcut for cramming. It is a delicate augmentation of the natural consolidation process. It works best when combined with structured wake learning, providing the raw material that sleep can then enhance. The dream of instant absorption remains fantasy, but the reality of subtle night learning is now firmly supported. 14. Emotional charge makes memories stick harder. Events that carry strong emotional tones are far more likely to survive the passage of time. The amygdala, an almond-shaped structure in the temporal lobe, tags such events and boosts the activity of the hippocampus during encoding. Stress hormones like norepinephrine flood the system, raising the likelihood that the trace will be replayed and strengthened during sleep. This mechanism is adaptive. In an unpredictable world, remembering danger and reward has higher survival value than remembering neutral details. It explains why people vividly recall where they were during shocking news, but cannot recall mundane tasks from the same day. The brain is tuned to prioritize what matters for survival and social navigation. Yet this advantage has a cost. Overtagging by trauma or chronic anxiety can overload the system, leaving intrusive memories that resist fading. Neutral context is forgotten while the emotional kernel burns too brightly. The same circuitry that saves lives can also burden them with scars that repeat at night and intrude during the day. Understanding this balance offers paths to intervention. Therapies that revisit emotional memories in safe contexts help re-encode them with reduced charge. Techniques that regulate stress hormones during and after events can shift how they are stored. The principle is clear. Emotion writes with indelible ink, for better or worse. 15. False memories can feel completely real. The act of remembering is reconstructive, not reproductive. Each recall blends traces with imagination, expectations, and suggestions from others. Under the right conditions, people can be led to believe they saw things that never happened. These false memories feel genuine because they activate many of the same brain regions as true ones. Experiments have shown that planting subtle cues can make participants believe they were lost in a mall as children or met someone who never existed. Brain scans reveal similar hippocampal activity for both real and fabricated scenes. Confidence and detail are not reliable guides. The mind's need for coherence can trump factual accuracy. False memory is not a rare glitch, it is a byproduct of a flexible system built for inference and imagination. That flexibility enables creativity, planning, and empathy. It also means eyewitness accounts are vulnerable. Two people who experienced the same event can diverge widely after repeated retellings or exposure to leading questions. The phenomenon raises questions about the reliability of personal history. Memory is not a photograph. It is a story continually edited, sometimes with outside influence. Accepting this does not weaken memory's value. It highlights its role as a living system designed for adaptability rather than perfect recording. 16. Faces and places use different memory routes. The brain distinguishes between categories of information. Faces are processed by specialized regions such as the fusiform face area, while places and scenes engage the parahippocampal place area. These regions link to broader networks that support recognition and recall. The division means that losing one route does not necessarily erase the other. This separation explains why certain injuries or conditions can produce selective deficits. A person might fail to recognize familiar faces, yet navigate spaces without issue, or vice versa. The modular architecture reflects evolutionary pressures. Recognizing individuals and understanding environments both held high survival value, but they required different types of analysis. The distinction also shows up in memory performance. People generally recall faces better when tied to context, such as where they were met. Places become more memorable when linked to emotional or social cues. The routes interact, but each has its own strengths. Training can leverage this by pairing categories across domains. Modern tools like fMRI confirm that these routes are not only functionally distinct, but physically localized. The brain devotes precious territory to handle these recurring tasks. Faces and places are anchors of social and spatial life, and memory systems reflect that importance. 17. Multitasking quietly erodes retention. Switching between tasks feels efficient but taxes working memory. Every shift forces the brain to clear one context and load another, leaving fragile traces vulnerable. Studies show that people who juggle multiple streams retain less detail and commit more errors when later tested. The illusion of productivity hides silent losses. The problem lies in divided attention. Memory encoding requires sustained focus to strengthen synaptic changes. When attention is split, encoding weakens. Even if tasks are completed, the depth of learning suffers. The next day, details evaporate and understanding feels shallow. The brain can only fully stabilize what it has room to attend to. Some people appear to multitask better, but they often rely on rapid serial switching rather than true parallel processing. The underlying limitation remains. Complex information that demands structure is the first casualty. Repetition cannot fully compensate if attention was never fully engaged. The solution is not always strict monotasking, but mindful structuring. Grouping tasks, setting intervals of uninterrupted focus, and reducing distractions all improve the quality of memory traces. Efficiency comes not from doing more at once, but from doing one thing with depth. Memory rewards the patient focus of sustained attention. 18. Stories last longer than lists. Narratives bind information into coherent arcs with beginnings, conflicts, and resolutions. The brain is naturally tuned to follow stories because they mirror the structure of lived experience. Lists lack this scaffolding, making them harder to recall without rehearsal. A story creates multiple retrieval cues while a list depends on order alone. Brain imaging shows that listening to stories engages not just language regions, but areas related to emotion, sensory imagery, and perspective taking. The more regions engaged, the stronger the network of memory becomes. A list of facts may fade quickly, but the same facts embedded in a story can last for years. This is why cultures transmit wisdom through myths and histories rather than raw instructions. The story format carries context, value, and emotion, which help anchor the knowledge. In education, storytelling methods often produce higher retention rates than traditional note delivery, even when the content is identical. Stories also aid personal memory. Framing daily events into a narrative helps consolidate them. Journaling that shapes experiences into stories creates a richer recall later. Memory is not just about facts, it is about how facts are woven into meaning, and stories provide the loom. 19. The brain forgets on purpose. Forgetting may seem like failure, but it is essential. The brain cannot hold every detail, so it actively discards to prevent overload. Synaptic weakening and pruning remove traces that are no longer useful. This process allows general patterns to remain without being buried under irrelevant clutter. Deliberate forgetting also serves emotional regulation. Painful details can be suppressed when they interfere with functioning. While suppression is not always complete, it reduces the ease of access. Over time, unused paths fade, and the memory becomes harder to trigger. This selective erasure supports resilience in the face of stress. Not all forgetting is equal. Some traces decay gradually, while others can be disrupted during reconsolidation when recalled. The system balances stability with flexibility, deciding what deserves to remain. This balance makes room for new learning, ensuring the brain is not trapped in the weight of its past. Seen this way, forgetting is not weakness. It is the hidden strength that allows focus on what matters now. Without forgetting, memory would be paralyzed by noise. The act of letting go clears space for the act of becoming. 20. Nostalgia can help the body and mind. Revisiting cherished memories is more than indulgence. Nostalgia boosts mood, raises self-esteem, and can even reduce the perception of physical pain. Warm recollections activate reward circuits and social bonding networks, releasing neurotransmitters that stabilize both mental and bodily states. A sweet memory becomes a form of internal medicine. Nostalgia works best when it connects to social ties. Remembering shared meals, music, or travels reactivates the sense of belonging, which buffers against loneliness. This social reinforcement is critical for resilience. People often turn to nostalgic memories during transitions, losses, or uncertainty because they restore a sense of continuity. Physical benefits emerge too. Positive recollection lowers stress hormone levels, improving cardiovascular and immune function. Experiments show that people exposed to nostalgic cues demonstrate greater tolerance to cold and pain, suggesting a direct bodily effect. The boundary between mind and body blurs as memory influences physiology. There is caution in excess. Dwelling too much on the past can block adaptation. The key is balance, using nostalgia as a resource rather than a refuge. When practiced wisely, it becomes a bridge that carries strength from the past into the challenges of the present. 21. Music can reach memories that speech cannot. Music bypasses many of the damaged roots in the brain and can stir fragments of identity even when words are gone. Alzheimer's patients who cannot recall their children's names may still sing lyrics to songs they loved as teenagers. Melodies and rhythms are stored and processed in widespread areas of the brain, not just in language centers. This gives them resilience when illness erodes speech and logic. The link between music and memory is ancient. Rhythmic chanting and song were humanity's first mnemonic devices long before writing. The repetitive structure of music engraves patterns more deeply than isolated facts. That is why we remember childhood rhymes effortlessly but struggle to recall lists of numbers. The brain's response to melody is built to hold and carry information. Modern therapy uses this resilience. Music therapy can restore lost skills, reduce agitation in dementia, and encourage speech and stroke patients through melodic intonation therapy. Singing forces language networks to reconnect with timing and pitch circuits, bypassing blocked roads with new detours. Music is not only art, it is a neurological tool. The power of music lies in its ability to awaken both emotion and structure. A song can revive forgotten moments with extraordinary vividness because it is linked to both feeling and pattern. In this way, music can keep parts of the self alive long after other memories fade. 22. Some people see nothing in the mind's eye. Aphantasia describes the inability to form mental images. When asked to picture an apple, some people see a clear image, others a vague outline, and those with aphantasia see nothing at all. They know what an apple is and can describe it, but their inner screen remains blank. This condition is more common than once thought, though most people with it never realize until asked. Despite lacking visual imagery, people with aphantasia often perform normally on memory tests. They rely more on abstract, verbal, or conceptual encoding rather than imagery. Their memories may feel less vivid, but no less accurate in terms of fact. This shows that memory is not one channel, but many, and that imagery is only one of its tools. Some aphantasic individuals report feeling less nostalgic or emotionally tied to visual memory, yet they can excel in fields that demand abstract reasoning, coding, or mathematics. Others develop compensatory strengths in language or logic. The condition demonstrates the diversity of how human brains store and retrieve experience. The discovery of aphantasia challenges the assumption that everyone's inner world looks the same. It opens questions about imagination, memory, and creativity. Do those without imagery dream differently? Do they navigate memory in words rather than pictures? The answers reveal how varied the human mind can be. 23. Others see with cinematic detail. At the opposite extreme lies hyperphantasia, the ability to imagine with lifelike vividness. People with hyperphantasia report inner visions so rich they feel indistinguishable from reality. For them, recalling a childhood bedroom can be like walking into it complete with textures, lighting, and sounds. This gift is striking, but it can also be overwhelming. Vivid imagery gives memory depth and clarity, but it also risks intrusion. Disturbing experiences can replay with sharpness that makes them hard to escape. The boundary between memory and imagination can blur, leading to difficulties when the mind loops on negative images. This intensity is both strength and vulnerability. Hyperphantasia aids creativity, art, and design. Many painters, writers, and inventors report strong visual imagination. It can also improve learning of spatial or visual material. Yet its presence is not required for creativity. Many great thinkers had ordinary or weak imagery. Memory is multimodal, and vividness is only one form of richness. The coexistence of aphantasia and hyperphantasia in the population shows the spectrum of how minds work. Some recall with words, some with faint shadows, some with vivid films. Each route has its own gifts and challenges. The diversity of memory styles is part of what makes human experience so varied. 24. A tiny jolt of surprise boosts learning. Surprise signals that the brain's predictions have failed. This error sparks dopamine release, which strengthens synaptic changes and marks the moment as important. A surprising detail in a lecture, an unexpected twist in a story, or an unusual pattern in numbers can all cement the memory more strongly than repetition alone. The brain is designed to learn when its models are broken. This process explains why routine fades quickly while anomalies stick. Ordinary commutes vanish, but the day something strange happened. On the road remains sharp. The brain stores what helps adjust its predictions. Surprise is not mere entertainment. It is fuel for adaptation. Educators and storytellers use this by weaving in unexpected shifts, humor, or contradictions. The disruption makes attention spike and memory networks seize the moment. Without such jolts, information slides past in a haze of familiarity. Surprise keeps the mind awake. The effect has limits. Too much surprise overwhelms and prevents integration, while too little leaves no trace. The balance between expectation and violation is what keeps memory strongest. In this balance lies the reason we seek novelty. It shapes how the brain remembers. 25. Memory loves spaces between study sessions. Cramming feels efficient but fades quickly. When learning is spread over time, the spacing effect strengthens recall. Each return to the material forces the brain to reconstruct the trace, deepening the network. The gaps allow partial forgetting, which paradoxically makes relearning more effective. This principle explains why distributed practice produces long-term retention. A single intense session may work for short tests, but days later much is gone. Several shorter sessions spaced over hours or days lead to memories that last weeks or months. The act of retrieval after a gap is the key. Spacing also aligns with natural cycles. Sleep between sessions allows consolidation and replay. Returning after rest means the memory has shifted locations, making the recall effort a fresh act of strengthening. Each session builds on a deeper foundation. The lesson is simple but profound. Forgetting is not failure during spaced learning. Forgetting creates the opportunity for memory to be rebuilt stronger. This is why habits, languages, and skills flourish with steady return, not desperate marathons. 26. Unfinished tasks linger more than finished ones. The Zeigarnik effect describes how incomplete tasks stay alive in the mind. When an action is started but not completed, the brain keeps it active as unresolved tension. This makes it easier to recall and harder to ignore. Once the task is completed, the tension drops and the memory often fades. Restaurants once exploited this effect. Waiters could remember long orders without writing them down, but once the bill was paid, the details evaporated. The brain had closed the loop. This mechanism conserves resources by keeping only active goals in high awareness. The lingering pull of unfinished tasks can be a burden. People may ruminate on incomplete projects or half-resolved conversations, finding them hard to release. But the same effect can be harnessed. Breaking work into smaller open steps can maintain momentum, since the brain resists leaving things unresolved. The Zeigarnik effect reveals a deeper rule. Memory is tied to goals, not just events. What matters is whether a story has reached its end. If the ending is missing, the mind keeps searching for it. 27. The brain prunes unused connections during sleep. While sleep strengthens some synapses, it also weakens others. Synaptic homeostasis theory suggests that daily activity builds countless small connections, many of them redundant. Sleep downscales these connections, trimming back excess so the network remains efficient. It is like a gardener cutting growth so the plant can thrive. Pruning prevents overload. Without it, the brain would drown in noise, with every weak trace competing for space. By scaling down globally, the brain keeps strong, important connections intact while removing clutter. This balance ensures learning without runaway energy demands. Pruning is not random. Synapses that were active during the day are tagged for preservation. Inactive ones are more likely to shrink. This creates a selective filter that rewards engagement and punishes neglect. What you attend to lives on, what you ignore fades. The pruning that occurs each night highlights how memory is an active balance between addition and subtraction. To learn is also to forget. Sleep provides the cycle that allows both processes to occur together. 28 microglia and complement tag synapses for removal. The immune system plays a hidden role in memory. Microglia, the brain's immune cells, patrol synapses and decide which ones to preserve or remove. They use molecular signals like complement proteins to tag weak or unnecessary connections for pruning. These microscopic judgments shape the architecture of learning. During development, this process is intense, carving out the adult brain from an overgrown tangle of connections. In adulthood, it continues more subtly, ensuring that memory networks remain flexible. Without pruning, circuits would become cluttered and inefficient. Problems arise when microglia overprune. Excessive activation by inflammation or stress can remove too many connections, weakening memory. This mechanism is thought to contribute to neurodegenerative disease. In contrast, insufficient pruning can cause disordered networks, linked to conditions like autism or epilepsy. The presence of immune processes in memory underscores that the brain is not separate from the body. Learning depends on cellular guardians making choices at the smallest scale, turning immune defense into sculptors of thought. 29. Astrocytes feed neurons to keep memories alive. Neurons do not work alone. Astrocytes, star-shaped support cells, provide energy, regulate chemicals, and maintain the environment neurons need. They shuttle glucose to neurons, recycle neurotransmitters, and buffer ions. Without their constant work, synapses would fail and memories could not stabilize. Astrocytes also influence information flow directly. They release gliotransmitters that modulate synaptic strength, effectively deciding how much communication passes between neurons. Far from passive, they are active partners in sculpting memory. Research shows astrocytes synchronize with neuronal networks during learning. Their calcium waves align with activity patterns, suggesting they help set the rhythm of plasticity. Damaging astrocytes disrupts memory, even if neurons remain intact, revealing their central role. Memory is not the product of neurons alone. It is the outcome of a community of cells, with astrocytes as crucial caretakers. The hidden helpers shape the persistence of thought as much as the firing neurons themselves. 30. Exercise raises a growth factor that protects memory. Physical activity increases levels of brain-derived neurotrophic factor, or BDNF, a protein that supports neuron survival, growth, and synaptic plasticity. BDNF is sometimes called fertilizer for the brain, as it strengthens connections and promotes the birth of new neurons in the hippocampus. The benefits of exercise on memory are seen across the lifespan. Children who move regularly perform better on learning tasks, and adults who maintain fitness preserve sharper cognition into old age. Even brief aerobic sessions can temporarily boost BDNF and improve memory performance. Exercise also reduces risk factors that impair memory, such as inflammation, stress hormones, and poor sleep. The cumulative effect is a brain that is more resilient to injury and disease. For neurodegenerative conditions, exercise may slow decline by maintaining plasticity longer. The message is simple. Movement is not just for muscles and heart. It is a direct intervention for memory health. Each step pumps growth signals into the brain, helping it renew and protect its capacity to remember. 31. The brain speeds up with better wiring. The nervous system does not rely solely on the number of neurons, but on how well they are connected. Each axon, the long fiber of a neuron, can be wrapped in myelin, a fatty sheath that insulates the signal and allows it to travel more quickly. Myelin turns a slow trickle of current into a rapid surge, letting information jump from node to node at high speed. When wiring improves, reaction times shorten, memory retrieval becomes smoother, and coordination feels effortless. This is why a skill that once felt clumsy can, after practice, feel automatic. The brain actively remodels its wiring in response to use. Regions that fire repeatedly during training attract thicker myelination, while unused paths thin out. This process is not just for childhood. Adults continue to refine their white matter structure throughout life, with intense learning or practice changing the physical speed of signals in months. Musicians, athletes, and bilingual speakers often show stronger white matter tracks in the regions they use most. Myelin repair is also crucial for resilience. Damage to myelin is seen in conditions like multiple sclerosis, where signal transmission becomes patchy and unreliable. The brain has cells called oligodendrocytes that can rebuild insulation, though their efficiency declines with age. Lifestyle factors such as aerobic exercise, sleep and nutrition can support myelin repair, indirectly sustaining cognitive clarity. The metaphor of wiring helps explain why repetition deepens memory. Every recall, every rehearsal is not just mental but structural. Neurons fire together, and their connections get wrapped tighter so that the next time the thought travels faster. In this way, practice literally rewires the speed of thought, building a more efficient brain. 32. Myelin changes with practice. When a skill is learned, whether playing piano, speaking a new language, or solving mathematical problems, the brain refines not only the grey matter where neurons live, but also the white matter where their long connections stretch. Repeated practice signals oligodendrocytes to thicken the myelin sheath around axons used in the skill. Over time, signals move with greater speed and precision, and the act becomes second nature. This is why highly trained individuals can execute complex sequences with astonishing smoothness. The importance of practice lies not in brute repetition, but in quality engagement. Focused practice, where attention is fully given to improvement, sends the strongest cues for myelination. Mindless repetition may still add some reinforcement, but it lacks the intensity that drives significant structural change. In other words, how you practice matters as much as how often. Myelin is also adaptive. If a skill is neglected, the associated tracks can thin, slowing signals and reducing accuracy. This does not mean learning vanishes completely, but that the brain prioritizes resources elsewhere. Relearning is faster than initial learning because traces remain, but the edge of speed can dull. The balance between use and neglect sculpts the myelin landscape across life. The story of myelin highlights that learning is not just about memory storage, but about signal flow. Every mental act depends on how efficiently networks talk to one another. When practice strengthens the sheath, the brain becomes not only better at recalling information, but better at moving it along its hidden highways. 33. The gut can whisper to memory networks. The brain and the gut share a two-way communication system through the vagus nerve and a swarm of chemical messengers. Bacteria in the intestines release metabolites that can cross into circulation, influencing inflammation, neurotransmitter levels, and even synaptic plasticity. This gut-brain axis means that what happens in the digestive tract can shape the very processes of memory and learning. Studies in animals show that altering gut microbiota changes performance in memory tasks. Diets rich in fiber and fermented foods foster bacteria that produce short-chain fatty acids, which in turn promote brain health. Conversely, disrupted microbiota from poor diet, antibiotics, or chronic stress can weaken hippocampal function. The gut acts as a quiet partner in the orchestra of memory, its rhythms resonating with the brain. The influence is not limited to chemistry. Signals from the gut can modulate mood, and mood shapes memory. A balanced microbiome can stabilize serotonin and dopamine levels, smoothing emotional swings and indirectly supporting better encoding and retrieval. When the gut falters, mood disorders and memory lapses often appear together. This connection challenges the idea that memory is confined to the skull. The nervous system is distributed, and health in one part of the system influences the whole. The gut's whispers may not tell stories, but they set the stage on which stories can be learned and recalled. 34. Heartbeats and breath, rhythm, shape, encoding. The timing of heartbeats and breathing does more than keep the body alive. These cycles also entrain brain activity, synchronizing oscillations that underlie attention and memory. A heartbeat can nudge neurons into excitability, making them more likely to encode a stimulus if it arrives at the right phase. Breathing in and out modulates rhythms in the hippocampus, altering how well information is registered. This coupling explains subtle effects. People may recall stimuli better if they were presented during inhalation rather than exhalation. Fear responses are stronger when triggered during certain heartbeat phases. Memory is not detached from the body's pulse, it is carried by it. The body's rhythms are like invisible metronomes guiding neural symphonies. Practices such as slow breathing, meditation, or yoga exploit this connection. By stabilizing respiratory cycles, they stabilize the oscillations that support memory consolidation. This is why deep breathing before learning or recalling can improve performance. not merely by calming stress but by aligning body and brain rhythms. These discoveries reveal that cognition is not purely cerebral. Memory is embodied, influenced by the heartbeat that pulses through veins and the breath that flows through lungs. The mind remembers better when the body's rhythms are in tune. By the way, if you like and subscribe to my video, this is the most effective way to support me. 35. The default mode network binds your story. When the brain is at rest, it is not idle. A set of regions called the default mode network, DMN, lights up, linking medial prefrontal, posterior cingulate, and parietal areas. This network supports autobiographical memory, self-reflection, and the weaving of personal narrative. It binds isolated episodes into the sense of an ongoing story, who you are, where you have been, and where you might go. The DMN activates when attention turns inward, daydreaming, recalling past events, imagining future scenarios. It connects time, emotion, and identity. Without it, memories would exist as scattered fragments. With it, they form chapters of a coherent life. It is the quiet author of the self, writing when focus shifts from the outside world. Disruptions to the DMN alter identity. Damage or disease can cause a fractured sense of self, where memories fail to line up into a stable story. On the other side, overactive DMN can feed rumination, where the mind loops on negative memories and predictions. Balance is crucial, allowing reflection without entrapment. The network's role underscores that memory is more than storage, it is narrative. The past is recalled not to replay facts but to make meaning. The DMN is the neural stage where the play of identity is performed, night after night and thought after thought. 36. The brain compresses reality to save space. Every waking moment floods the nervous system with sensory input. Colours, shapes, sounds, textures, movements, emotional tones. If the brain tried to record each detail as it is, it would quickly run out of capacity. Instead, it compresses. Like a skilled editor, the brain keeps the essentials and discards redundancy, packaging hours of experience into a manageable summary. This is why a busy street full of unique faces becomes remembered as a crowded sidewalk, and a long lecture might be recalled as a talk about memory science. Compression allows us to live in real time without drowning in data. The hippocampus and surrounding cortical areas play a central role in this editing. They detect patterns, remove repetitions, and store only the meaningful distinctions. For example, if you look at 100 nearly identical chairs in a hall, your brain does not remember each one. It encodes the category rows of chairs and maybe the one with a broken leg. This system ensures efficiency but also explains why we often miss fine details that were technically present at the time. Compression also gives rise to illusions of time. Days that are filled with novelty seem long because many unique patterns are stored. In contrast, days filled with routine compress into a blur, which makes them feel short in retrospect. Vacations feel long because they overflow with distinct memories, while work weeks vanish into the fog of similarity. The compression system not only saves storage but shapes our perception of time itself. Understanding this process has practical value. If you want to make events memorable, you must break routine and introduce variation. A change in route, a new flavour, a surprising conversation, all prevent compression and increase storage. The brain remembers what stands out. It does not save everything, it saves what breaks the pattern. 37. Attention blinks can erase what is right there. When the brain locks onto a stimulus, there is a brief refractory period in which new stimuli cannot be properly encoded. This phenomenon is called the attentional blink. If two important signals occur within a fraction of a second, the second is often missed entirely, as if it never existed. For instance, when scanning a stream of rapidly flashing numbers, you may see the first target clearly, but be blind to the seconds if it arrives too quickly afterward. The attentional blink shows that attention is not a continuous spotlight but a rhythmic pulse. Neurons that process the first stimulus must recover before the system can fully respond again. During that recovery, the sensory input still arrives, but it is not encoded into conscious awareness or memory. In effect, the brain chooses depth over breadth. It processes one event deeply at the cost of ignoring what comes next. This limitation has real-world consequences. When driving, if you focus intensely on a sudden hazard, you might miss another hazard that follows seconds later. In learning environments, if too much information is presented in rapid succession, large portions vanish during blinks. The mind protects itself from overload by narrowing, but the narrowing leaves blind spots. Designing experiences that respect these rhythms helps memory. Presenting key material with short pauses in between allows attention to reset. Meditation and mindfulness training can extend the brain's tolerance, making the blink shorter or less disruptive. Knowing that our perception is punctuated reminds us that missing details does not always mean carelessness. It is how the system is built. 38. Change blindness hides huge differences in scenes. When two images are presented with only slight differences, people often fail to notice even major changes if they occur during a brief interruption. A building might disappear from a photo, a person's shirt colour might change, and yet observers stare without registering the alteration. This is called change blindness, and it highlights how much we rely on memory assumptions rather than continuous perception. The visual system does not store every pixel. It samples key points and relies on prediction to fill in the rest. As long as the scene is broadly consistent, the brain assumes stability. This efficiency prevents overload but leaves us vulnerable to missing what is right before our eyes. Our confidence in seeing everything is often an illusion. Change blindness is not just a laboratory trick. In daily life, people can fail to notice a new sign on a familiar street, or even fail to recognize when a person they are speaking with is silently swapped out by another actor in a staged experiment. The mind expects continuity and resists updating unless the change is flagged as important. This limitation explains why eyewitness testimony can be unreliable. It also reminds us that attention is selective and memory is reconstructive. Perception is a partnership between the external world and internal expectation. When the expectation is too strong, change can slip through unseen. 39. Context holds the key to recall. Memories are not floating files that can be summoned at will. They are bound tightly to the context in which they were formed. The sights, sounds, smells, and even emotional states present at the time of learning serve as cues. When those cues are absent, retrieval can feel impossible. When they are recreated, memory often flows effortlessly. This is called context-dependent memory. For example, divers who learn words underwater recall them better underwater than on land. Students who study in a room and then take a test in the same room often perform better than those tested elsewhere. The context provides hooks that help the hippocampus reconstruct the original experience. Without hooks, the brain must guess at which network to activate. Context also includes internal states. Memories formed while happy are more accessible when happy again. The same is true for sadness, stress, or calm. This state-dependent recall explains why some problems seem unsolvable until a mood shift occurs, at which point the solution suddenly appears. The brain retrieves selectively based on state. The lesson is clear. If you want to recall information reliably, vary the context in which you learn. Studying in different places or moods provides multiple retrieval paths, making the memory more robust. Context is not decoration, it is part of the memory itself. 40. Returning to a place can bring a memory back. Stepping into a childhood home often stirs details that seemed lost forever. This is because the original spatial and sensory cues reappear, reactivating the networks in which the memory was encoded. The hippocampus, with its place cells and grid cells, treats location as a central organizing principle. Returning to the location provides the skeleton upon which the rest of the memory can be reconstructed. This effect is so strong that even partial cues, like the smell of the wood in the hallway or the creak of the stairs, can bring floods of images and feelings. The brain does not store events as isolated data points, but as webs tied to place. When the web is touched in the right spot, the rest lights up. This mechanism is also why virtual reality environments can enhance learning or therapy. Immersive simulations recreate enough of the original context to trigger recall and allow for updating memories with new, safer associations. In exposure therapy for trauma, returning virtually or physically to the place of fear can allow the memory to be rewritten with calmer outcomes. The principle that place unlocks memory shows why wandering back through old environments can feel like time travel. The stones, smells, and sounds are not just scenery, they are keys to the locks of the past, waiting to be turned. 41. Bilingual minds build tougher memory scaffolds. Learning and using more than one language forces the brain to maintain multiple systems of grammar, vocabulary, and social context. This juggling strengthens executive control networks and the ability to switch between tasks. Over time, bilingual individuals often show more resilient memory performance, especially against age-related decline. The constant switching acts like a workout for the frontal and hippocampal systems. The advantages extend beyond language. Bilinguals tend to perform better on tasks that require ignoring irrelevant information and focusing on the target. This inhibitory control spills over into memory, allowing them to resist interference when recalling details. Their memory scaffolds are tougher because they are used to managing competition. The benefits appear across the lifespan. Children raised in bilingual environments often show greater mental flexibility, while older adults show delayed onset of dementia symptoms. The act of navigating multiple codes builds redundancy into the system, making it harder for disease to collapse the whole structure. This does not mean monolinguals are at a disadvantage in all areas, but it highlights how memory thrives on challenge. The bilingual brain demonstrates that complexity, far from being a burden, can be a shield. By stretching, the system becomes more resilient, carrying its strength into age. 42. Childhood amnesia hides the earliest years. Most people cannot recall events from before the age of 3 or 4, a puzzle known as childhood amnesia. The memories were once present, yet they do not survive into adulthood. Scientists believe this occurs because the hippocampus and prefrontal cortex, two key structures in memory formation, are still under construction during those years. Experiences are encoded, but the circuits that allow stable long-term retrieval are immature, and so the early traces fade. Language development plays a role as well. Memories are easier to stabilize when there is a verbal scaffold to attach them to. A toddler may live a vivid day, but without the words to describe it, the encoding remains fragile. As language expands, the brain can use words as cues, but by then many pre-verbal memories have already dissolved. This explains why fragments of very early life may sometimes survive if they were tied to strong emotions or repeated a family stories that acted as later cues. The phenomenon reminds us that forgetting is as natural as remembering. The brain sacrifices the earliest traces in order to build a system capable of handling a lifetime of data. Those lost years are not empty, however. They shape emotional and cognitive development in ways that persist beneath conscious recall. The rhythm of speech heard from parents, the safety of touch, the presence or absence of stress, all of these leave lasting marks on the nervous system even if the stories vanish. Childhood amnesia is both loss and foundation. We cannot revisit the first years in detail, but we live with their effects every day. They are the soil out of which later memory grows, silent yet powerful. 43. Early life stress leaves long memory shadows. Stress during early childhood has effects that can echo across decades. When the developing brain is exposed to repeated surges of cortisol and other stress hormones, the hippocampus and amygdala may grow differently. The hippocampus can be stunted, reducing the ability to form stable episodic memories, while the amygdala may become overactive, leading to heightened emotional reactivity. These changes can alter how memories are stored and retrieved throughout life. The shadow of early stress is not limited to cognitive function. It also affects vulnerability to mental health conditions. Adults who experienced chronic adversity as children often show greater risk of depression, anxiety, and post-traumatic stress disorders. Their memories of negative events may feel more intrusive, while positive memories may be less accessible. The imbalance between what is remembered and what is forgotten can tilt mood and decision-making. Neuroplasticity provides some hope. Supportive relationships, therapy, and enriched environments can help remodel circuits and reduce the weight of early scars. The brain remains capable of growth, and even damaged hippocampal networks can be strengthened through learning and positive experience. The shadow can fade, even if it never disappears completely. The persistence of these effects shows how deeply memory is woven with development. Early experiences are not simply forgotten once childhood passes. They shape the architecture of the brain itself, influencing how every later memory will be handled. 44. Trauma can freeze the sense of time. For survivors of traumatic events, memory can feel very different from ordinary recall. Instead of fading into the past, the memory can remain vivid, intrusive, and timeless, as if it is happening again in the present. This happens because the circuits that normally place events into chronological order, the hippocampus, are disrupted by overwhelming stress hormones, while the amygdala floods the system with signals that say, "This must never be forgotten." As a result, traumatic memories may be fragmented, lacking clear beginning or end, but loaded with sensory detail. A sound, smell, or visual cue can trigger the network, causing the individual to re-experience the moment with full emotional force. This is not imagination, it is the memory network firing without proper temporal tagging. Time is lost, and the past invades the present. This phenomenon explains symptoms of post-traumatic stress disorder, where flashbacks and nightmares dominate. Therapies that aim to re-anchor the memory into time, such as exposure therapy or eye movement desensitization and reprocessing, help by engaging the hippocampus again, allowing the memory to be re-encoded with a clear boundary of then and now. The memory does not vanish, but it becomes part of the past instead of a constant present. Trauma shows the dual edge of memory. The same machinery that makes survival events unforgettable can also imprison a person within them. Healing requires not erasure but transformation, turning the frozen fragment back into a story that belongs to history. 45. Memory and imagination share the same engine. When you recall the past or imagine the future, the brain activates overlapping circuits. The hippocampus, which binds episodes together, lights up whether you are replaying yesterday or simulating tomorrow. This overlap shows that memory is not only a record, but also a tool for building possibilities. The same patterns used to reconstruct what has been are borrowed to predict what might be. This is why imagination feels so real. When you think of walking down a beach you have never visited, your brain recruits real sensory and spatial memories, weaving them together into a plausible scene. Similarly, when you plan a conversation, you draw on past dialogues and piece them into a rehearsal. Imagination is memory repurposed. The overlap has advantages and costs. It allows humans to plan, innovate, and dream, but it also opens the door to confusion between real and imagined events. False memories may arise when imagination is vivid enough to be mistaken for reality. The boundary between what was and what might be is thin because the same system is doing both jobs. The recognition of this shared engine changes how we view memory. It is not a fixed archive, but a living workshop. Every act of recall is also an act of creation, whether of the past, the present, or the future. 46. The brain invents reasons when memory fails. When memory falters, the brain often fills the gap with plausible fabrications, a phenomenon known as confabulation. This is not deliberate lying. It is the automatic attempt of the mind to maintain coherence. Patients with frontal lobe damage or certain forms of amnesia may describe events that never happened with great confidence because their brain is trying to explain missing links. Even in healthy individuals, small confabulations occur. When recalling a list, we may insert a word that fits the theme but was never present. When recounting a story, we may unconsciously add details to make it flow. The brain values narrative consistency over factual precision. A memory with gaps feels wrong, so the system fills them to restore order. This tendency is adaptive in everyday life. By smoothing over gaps, the brain avoids paralysis and maintains continuity of self. However, it can become dangerous in settings like eyewitness testimony or medical decision-making, where accuracy matters. Confidence should not be confused with correctness. The phenomenon reveals memory's true nature, not a camera, but a storyteller. And like any storyteller, the mind sometimes improvises. What feels like truth may be a carefully woven patch. 47. Highly vivid memory has hidden costs. Some individuals, a handful in the world, live with highly superior autobiographical memory. They can recall what they were doing on nearly any given date, down to the weather and the clothes they wore. Their memories are so detailed that they can relive decades of life as if flipping through a diary with perfect pages. To outsiders, this seems like a gift beyond measure, yet those who live with this ability often describe burdens. The constant flood of memories can be distracting, pulling attention into the past when focus is needed in the present. Negative experiences are not softened by forgetting. They remain as sharp as the day they occurred, replaying with full emotional intensity. The gift of total recall becomes a prison of endless replay. Scientific studies show that their brains are not fundamentally different in structure, but may have differences in connectivity or strategies that allow retrieval on command. What makes them unique also makes them vulnerable to obsession and difficulty moving on from pain. The ordinary forgetfulness most of us live with is in fact protective. This rare condition underscores that memory is not better when it is perfect. The balance of remembering and forgetting creates the space for healing, growth, and forward movement. The ability to let go is as vital as the ability to hold on. 48. The sense of ownership over memories can be tricked. Experiments show that people can be led to believe they experienced events that actually happened to someone else. Subtle suggestion, doctored photographs, or narratives told with confidence can implant a sense of personal ownership. The brain's source monitoring system, which tracks where information came from, is fallible. When it slips, borrowed memories become indistinguishable from lived ones. This trickery is not confined to laboratories. In families, stories told repeatedly can become part of a person's identity, even if they never lived them. "You were always scared of dogs as a child," repeated often enough, may be accepted as truth. Memory ownership can be transferred by social reinforcement. The phenomenon reveals the social nature of memory. We do not remember alone, we remember in groups, influenced by the narratives around us. This enriches identity, but also makes it porous. The mind values coherence more than strict accuracy, and so it sometimes welcomes memories that are not truly ours. The fragility of ownership shows why skepticism is essential. Memories may feel deeply personal, but they are built-in networks that include other voices. Our life stories are part autobiography, part collaboration. 49. Mirror systems echo the acts of others. In the premotor cortex and parietal lobe, scientists have identified neurons that fire both when we perform an action and when we observe someone else performing it. These mirror neurons provide a direct resonance with the behavior of others. When you see someone grasp a cup, neurons in your own motor system activate as if you were preparing to grasp it. This mirroring lays a foundation for empathy and imitation. Memory is shaped by this system. By observing others, we encode motor patterns into our own neural circuits. This is how infants learn, by copying, and how adults acquire skills by watching experts. The memory of action is not only built by doing, but also by seeing. The brain rehearses movements simply by exposure. The mirror system also extends to emotion. Observing facial expressions can trigger neural activity associated with feeling that emotion yourself. This resonance strengthens social learning as the brain builds memory of how emotions are expressed and what they mean. Social bonds are reinforced by this invisible echoing. The existence of mirror systems suggests that memory is never private. Every interaction leaves traces of others within us. To remember is also to carry the gestures, actions, and emotions of the people we observe, woven into our own circuits. 50. Skill memory sits on a different track. The brain distinguishes between declarative memory, facts and events, and procedural memory, skills and habits. Procedural memory relies heavily on the basal ganglia and cerebellum, regions that coordinate action sequences. Once a skill is learned, such as riding a bicycle or typing on a keyboard, it can persist even when declarative memory is impaired. Patients with amnesia can still learn new motor skills without recalling the lessons. This separation gives skill memory remarkable durability. It explains why musicians can still play familiar pieces even after losing much of their explicit recall. It also shows why habits, once ingrained, are difficult to break. The circuits that store them operate on a more automatic, less flexible plane than the circuits of episodic memory. Skill memory is refined through repetition and feedback. Each practice strengthens synaptic pathways in the motor system, building automaticity. Over time, the skill becomes less dependent on conscious attention. This frees cognitive resources for other tasks but makes unlearning more difficult. The brain prefers to refine skills rather than erase them. The dual-track system is a safeguard. Even when illness erases stories and facts, the body often retains its skills. Memory is not one thing but many. In the quiet persistence of procedural memory, the brain shows its ability to carry part of us forward even when other parts falter. 51. The cerebellum helps think as well as move. For much of history, the cerebellum was seen purely as the coordinator of movement, the hidden conductor that allowed muscles to act smoothly and posture to remain stable. Yet modern research shows that this densely packed structure, holding more than half of the brain's neurons, also plays a role in cognition and memory. The cerebellum helps predict the consequences of actions not only in the physical world, but in abstract reasoning. When you anticipate how a sentence will end, or when you mentally rehearse a conversation, The cerebellum is quietly running simulations. This predictive capacity shapes memory because it tunes timing and sequence. Just as the cerebellum keeps a pianist's fingers aligned in rapid succession, it also helps order the sequence of thoughts. When patients suffer damage to the cerebellum, they often show not only clumsy movements but difficulty in planning, language, and recalling ordered events. The system that once seemed only mechanical reveals itself as a partner in thought. The cerebellum also influences learning by sending feedback loops into the frontal and parietal lobes. Each loop carries signals about error correction, refining not just muscle memory but also problem-solving strategies. This explains why practice in complex skills such as sports or music strengthens not only movement but general cognitive flexibility. The cerebellum is a master of adaptation, ensuring that mistakes become lessons. Seeing the cerebellum as part of thinking expands the picture of memory. It is not only the hippocampus and cortex that encode the past. The rhythms of movement, the corrections of error, and the quiet simulations of possibility all come from the cerebellum, weaving motor precision with the fabric of mental life. 52. Music training reshapes auditory memory. The brain of a trained musician looks and functions differently from that of a non-musician. Years of practice carve out sharper responses in auditory cortex regions, allowing subtle distinctions in pitch, timing, and rhythm. These changes extend beyond music into language learning, emotional perception, and even memory of spoken material. The brain's musical training fine-tunes the ability to remember complex auditory streams. Neuroimaging shows that musicians have denser connections between auditory and motor areas. These pathways allow rapid recall of sequences, whether musical notes or linguistic syllables. Their memory is not only broader but more precise, capable of distinguishing microsecond differences in timing. This auditory acuity strengthens working memory as well, since the brain must hold and manipulate more fine-grained information at once. The benefits of musical training often last a lifetime. Older adults who once studied an instrument can show slower cognitive decline and better memory for verbal material than peers who did not. Music acts as long-term enrichment, leaving a structural trace in the brain. It is not simply an art form but a form of cognitive exercise. This evidence explains why music has been linked to academic achievement. By shaping the auditory memory system, training builds a brain that is better at detecting, encoding, and recalling patterns. Every scale practiced and every rhythm repeated rewires the memory system to hold the ephemeral world of sound with lasting strength. 53. Smiling shifts chemistry that helps memory. The simple act of smiling changes the body's neurochemistry. Muscles in the face send signals to the brain that release dopamine and serotonin, two neurotransmitters tied to reward and mood regulation. These chemical shifts influence the hippocampus and prefrontal cortex, regions central to memory encoding. A smile, even when forced, can tilt the brain toward receptivity, making learning easier and recall more durable. This effect illustrates how emotion and cognition intertwine. Positive mood broadens attention and increases the likelihood that information will be encoded. People who smile during study often recall more than those who approach the task with neutral or negative expressions. The physical act of smiling signals the nervous system to treat the environment as safe and rewarding, reducing stress chemistry that interferes with memory. Smiling also influences social memory. When two people exchange smiles, oxytocin release enhances bonding, and the memory of the interaction becomes more salient. Relationships are remembered not only for what is said but for the emotional tone. A genuine smile engraves itself deeper than words because it taps into primal reward circuits. The message is small yet profound. Mood states are not passive. By shifting them through simple behaviors like smiling, we alter the very landscape of memory. What we remember is partly a reflection of the expressions we wear. 54. Laughter can prime the brain to remember. Laughter is more than amusement. It triggers bursts of dopamine, the neurotransmitter that signals reward and novelty. When dopamine surges, the hippocampus becomes more plastic, meaning synapses are more likely to strengthen. A joke before a lesson or a shared laugh in a conversation can increase the chances that the material will be remembered. Humor is not just social glue, it is a mnemonic device. Brain scans reveal that laughter engages widespread regions, from frontal decision-making circuits to limbic emotional centers. This broad activation creates multiple pathways for encoding. When an idea is tied to laughter, it gains entry into a network of emotion, context, and novelty. Later, when the laughter is recalled, the idea resurfaces as well. The social aspect of laughter adds another layer. Shared humour builds group identity and collective memory. Memory is written in the forest of dendritic spines. These spines are dynamic. In live imaging experiments, researchers watch them appear within hours of training. Some last days, others weeks, depending on how often they are reactivated. The more a memory is recalled, the more stable its spines become. Forgetting occurs when spines retract, erasing the path of communication. The plasticity of spines explains both the fragility and the adaptability of memory. Fragility, because unused connections dissolve quickly. Adaptability, because new spines can sprout whenever novelty appears. This balance allows the brain to remain flexible while keeping essential knowledge. The growth of dendritic spines is fueled by proteins and energy. This is why nutrition, sleep, and oxygen supply matter. Learning is not abstract, it is biological work, carving microscopic protrusions that hold the shape of thought itself. 59. Neurons that fire together wire together. This simple phrase captures one of the most important rules of memory, Hebbian plasticity. When two neurons are repeatedly active at the same time, the connection between them strengthens. The next time one fires, the other is more likely to fire as well. Over time, entire networks are sculpted by these patterns of co-activation. This is how associations form and why repetition engraves knowledge. The strengthening occurs at synapses, where neurotransmitter release increases and receptor density changes. Dendritic spines enlarge, making the connection more reliable. Conversely, when neurons do not fire together, the link weakens. The brain invests in what is used and abandons what is not. This principle is seen everywhere, from simple reflexes to complex ideas. A child learning to associate letters with someone strengthens neural ties with each reading session. An athlete linking movements into a routine reinforces pathways with every practice. Memory is not stored in isolation, but in the choreography of firing neurons. The rule also explains habit formation and bias. When thoughts or actions are repeated, even unintentionally, their circuits grow stronger. This is why changing behavior requires deliberate effort to weaken old links while forging new ones. Memory is shaped by repetition as much as by novelty, one firing at a time. 60. Prediction errors drive the strongest updates. The brain is a prediction machine. It constantly generates models of what should happen next and compares them to reality. When reality matches expectation, little changes. But when a prediction error occurs, learning spikes. Dopamine floods the system, marking the moment as important, and synapses shift to incorporate the new information. Surprise is the sculptor of memory. This explains why routine fades but anomalies last. A day when everything goes as expected is barely remembered, while a single unexpected event stands out years later. The error between prediction and reality drives consolidation. The larger the gap, the stronger the trace, up to the point where overwhelming shock can impair encoding entirely. Prediction errors are critical in skill learning. When a tennis player expects the ball to move one way but it curves differently, the error forces adjustment and strengthens memory of the new technique. Without error, practice would not refine ability. Memory grows when models break. This system also applies to belief and knowledge. When deeply held assumptions are contradicted by experience, the discomfort is high, but so is the opportunity for change. The nervous system is wired to notice when it is wrong. Error is not failure, but the engine of growth. 61. Schemas make new facts stick faster. The brain does not treat every piece of information as brand new. Instead, it organizes knowledge into schemas, mental frameworks that define how things usually work. When new information fits a schema, it is absorbed quickly, anchored by existing structures. A child who already understands what a dog is will learn the word poodle much more easily than a child with no concept of animals at all. Schemas give memory a skeleton, and new facts become flesh on that skeleton. This system is efficient but also selective. When information clashes with an established schema, it is harder to learn, often resisted or distorted to fit pre-existing models. This explains why people sometimes misremember events to match their expectations. Schemas smooth recall but can introduce bias, bending details toward what is already believed. Schemas are not static, they evolve as experiences accumulate. When enough anomalies build up, the brain reshapes the framework to accommodate them, like a scientist adjusting a theory after new data arrives. This ability to revise is what allows learning to scale beyond rote fact collection into true understanding. The use of schemas shows how memory is not a flat list but a living network. Knowledge grows fastest when it attaches to what is already there, and the richness of schemas determines the richness of new learning. The past structures the future not only in stories but in the scaffolds of thought itself. 62. Memories can be updated during a brief window. When a memory is recalled, it does not simply play back like a recording, it enters a labile state temporarily unstable before being restored in a process called reconsolidation. During this fragile window, which can last hours, the memory can be altered, strengthened, or weakened. New information can be woven in, and old details can be lost. This process has profound implications. Therapies for trauma often rely on reconsolidation, reactivating painful memories and then introducing calming or corrective experiences. When the memory is restored, it carries the new emotional tone. Similarly, studying material and then revising it immediately after recall can lock in stronger versions of knowledge. Reconsolidation explains why memories are so malleable. Each act of remembering is also an act of rewriting. Confidence in memory does not equal stability. A recalled story may drift further from the original every time it is told, because each retelling offers a new chance for modification. The fragile window is both risk and opportunity. It means that memories can be corrupted, but it also means that harmful ones can be healed. The past is not set in stone, it is clay, softened whenever it is touched, ready to be reshaped before it hardens again. 63. Some genetic marks carry memory of fear. Experiments in animals suggest that experiences of stress or fear can leave molecular tags on DNA that are passed to offspring. This field, known as epigenetics, shows that memory is not only neural, but also biological inheritance. When a mouse learns to fear a certain odor, its children may show heightened sensitivity to the same odor, even if they never encountered it before. The experience left marks on the germline that carried forward. This does not mean detailed memories are inherited. Rather, it means that heightened readiness for certain responses can cross generations. The hippocampus and amygdala in the offspring are more primed for fear, creating a baseline of vigilance shaped by the parent's experience. It is as if the nervous system whispers warnings across time. The implications for humans are still being explored, but there is evidence that descendants of people exposed to trauma, such as famine or war, show altered stress responses and memory function. The body may carry echoes of ancestral events, shaping vulnerability and resilience. This blending of biology and memory complicates the idea of self. What we remember may not start with us. The nervous system inherits tendencies, tuned by the struggles of those before us. In this sense, memory is not only personal but ancestral, passed in molecular shadows. 64. Culture itself is a memory organ. Human culture functions as an external memory system, storing knowledge across generations in language, writing, art, and ritual. No single brain can hold the vastness of accumulated knowledge, but together societies create systems that preserve it. Libraries, oral traditions, and digital archives act as extensions of the hippocampus, keeping memories alive beyond individual lifespans. This externalization shapes how internal memory develops. Literate societies emphasize abstract and symbolic memory, while oral societies emphasize rhythm, repetition, and story. A person raised in one culture remembers differently than a person raised in another, because the tools of memory differ. Culture molds the architecture of thought. The relationship is reciprocal. Culture does not just store memory, it creates it. Shared rituals, national myths, and collective histories give people a framework within which to place personal stories. Memory becomes collective, held in groups as well as individuals. What one remembers is influenced by what the community chooses to remember. Culture as a memory organ shows how fragile knowledge is. When languages vanish or traditions are broken, vast libraries of popular memory disappear. Preserving culture is preserving human memory itself, ensuring that the past remains accessible for the future. 65. Memory is the mind's most creative act. The common belief is that creativity and memory are separate. One retrieves the past, the other invents the new, yet neuroscience shows they are inseparable. To imagine, the brain recombines pieces of memory, weaving fragments into new patterns. Every poem, invention, or idea is a remix of what has been remembered. Memory is not passive storage, but active creation. When an artist paints a landscape, they draw on stored visual scenes, emotional tones, and techniques learned through practice. When a scientist forms a hypothesis, they rely on remembered data, analogies, and past failures. Even daydreams are constructed from the building blocks of memory. Without memory, imagination would have no raw material. The act of recall itself is creative. Each time a memory is retrieved, it is reconstructed, often altered, and then stored again in its new form. Over time, this process makes memories less like fixed snapshots and more like evolving stories. They shift with perspective, blending with other memories and sometimes producing entirely new narratives. This creative aspect of memory is what allows humans to adapt. A perfect archive would trap us in the past. A flexible, creative memory gives us the ability to face novelty with the lessons of history reshaped for the present. Memory is invention as much as recollection. 66. Fear memories can pass down through generations. When an organism encounters danger, the memory of that threat is encoded in the amygdala and hippocampus. But research shows that the consequences can extend further, altering gene expression in ways that affect offspring. Descendants of animals exposed to predators or harsh environments often display heightened vigilance, as if they inherited the fear itself. This transgenerational effect is not the memory of specific events, but the readiness for certain responses. It represents the nervous system preparing the next generation for a world it has never seen. The hippocampus of the offspring shows altered synaptic plasticity, and the stress hormone systems are more reactive. The memory of fear has become biological inheritance. For humans, the evidence is complex but compelling. Children and grandchildren of trauma survivors often show heightened stress sensitivity, even when raised in safe conditions. Their bodies carry traces of events they did not live through. This blending of memory and biology raises profound questions about identity and resilience. The inheritance of fear reveals memory as a system that extends beyond one lifetime. What is remembered in one generation shapes the physiology of the next. Memory is not only a personal story, but a family legacy written into the very molecules of life. 67. Meditation alters brainwaves, improving memory stability. Meditation practices slow the brain's rhythms, producing waves that resemble those of early sleep. These states promote relaxation and reduce stress hormones, but they also affect memory consolidation. The hippocampus and prefrontal cortex synchronize more smoothly, allowing memories to be encoded and stabilized with less interference. Functional imaging studies show that experienced meditators have thicker cortical regions involved in attention and memory. The daily repetition of focusing, letting go, and returning builds neural resilience. Stress reduction enhances the survival of new neurons, and improved attention sharpens encoding. Meditation thus shapes memory both directly and indirectly. The benefits extend to emotional memory. Mindfulness practices reduce the intensity of negative recall, preventing rumination. Instead of looping on painful memories, meditators report seeing them with detachment, which weakens their emotional grip. This allows learning from the memory without being trapped by it. Meditation demonstrates that memory is not fixed. By changing daily mental habits, the nervous system reshapes its rhythms and rewires the strength of its connections. The simple act of sitting in stillness becomes a tool for rewriting how the past is held and how the present is learned. 68. Multitasking weakens memory retention. When attention is split between tasks, encoding suffers. The hippocampus relies on focused engagement to strengthen synapses. Dividing attention means neither task receives the depth needed for long-term memory. The illusion of productivity hides the fact that details are slipping away. A student checking messages while studying feels busy but remembers less. The problem is not only distraction but switching costs. Every time the brain shifts tasks, it clears one context and loads another, which disrupts fragile traces. The constant resetting prevents the consolidation of details. Even brief interruptions, such as glancing at a notification, can cause measurable drops in recall. Some people appear adept at juggling tasks, but this is usually rapid serial switching rather than true parallel processing. The underlying limitation remains. Working memory is overloaded, and long-term memory formation falters. Complex or abstract material suffers the most, while shallow tasks can survive. The lesson is that memory thrives on depth. To build lasting knowledge, attention must be given fully. Multitasking may feel efficient, but it writes weaker traces. Focus is the hidden ally of memory, turning fleeting moments into durable structures. 69. The flashbulb memories of shocking events often degrade with time. People often believe that they remember exactly where they were and what they were doing when dramatic events occurred, such as natural disasters or historic tragedies. These are called flashbulb memories, and they feel vivid and permanent. Yet careful studies show that over time, the details degrade and distort just like ordinary memories. The confidence remains high, but accuracy falls. The vividness comes from an emotional arousal. The amygdala tags the event as important, and dopamine surges engrave the initial impression strongly. But without repeated rehearsal and context reinforcement, the details blur. People misremember who they were with, what was said, or even where they were, while remaining absolutely certain of their version. Flashbulb memories reveal the gap between confidence and truth. They are socially powerful because communities rehearse them together, reinforcing collective versions of the story. These rehearsals can overwrite individual details, creating shared but inaccurate histories. The phenomenon teaches humility. Even the most vivid, emotionally charged memories are not photographs. They are reconstructions, subject to change. Trusting them blindly risks mistaking confidence for accuracy. 70. Collective memory shapes entire cultures. Memory does not only belong to individuals. Communities build collective memory through rituals, monuments, histories, and myths. These shared recollections define identity, creating a sense of belonging and continuity. Nations remember wars and victories. Families remember ancestors. Religions remember revelations. Memory at the group level is as real and influential as memory at the personal level. Collective memory guides behavior. It tells societies what to celebrate, what to fear, and what to avoid repeating. It also creates conflict when different groups remember the same events differently. The past becomes contested terrain, not only of history books but of living identity. This memory is maintained by institutions. Schools, media, and political leaders shape how stories are told, which parts are highlighted, and which are forgotten. The act of forgetting is as political as remembering. What a society chooses to erase is as telling as what it preserves. By studying collective memory, we see how the brain scales upward. The same processes of selection, distortion, and storytelling occur at the cultural level. Memory, whether personal or collective, is not just about accuracy, but about meaning. 71. The brain may prioritize survival memories over happiness. When resources are limited, the nervous system chooses what to keep. Survival-related events are far more likely to be remembered than neutral or even joyful ones. This bias is built into the amygdala, which tags fear, threat, and danger for stronger encoding. A single frightening encounter with an animal may stay vivid for a lifetime, while dozens of peaceful afternoons may blur into a haze. The system is designed to keep us alive, not necessarily content. This prioritization explains why negative events often dominate recall. It is not weakness but design. Remembering danger is protective, yet the weight of such memories can distort perception, making the world feel more threatening than it is. The balance between remembering risk and recalling joy is delicate, and in some individuals, it tilts too far toward fear, contributing to anxiety or trauma. The survival bias does not mean happiness is forgotten entirely. Positive experiences tied to bonding, love, or achievement also survive well, because they carry survival value in social terms. Evolution favored the storage of memories that enhance safety and reproduction, whether through avoiding harm or securing connection. Understanding this bias gives perspective. If negative memories feel sharper, it is not necessarily a flaw in personality. It is the nervous system doing its job. Deliberate focus on positive recall, such as gratitude practices, helps counterbalance the bias, ensuring that joy is given space alongside survival. 72. Long-term stress kills neurons in the hippocampus. The hippocampus is especially sensitive to cortisol, the hormone released during prolonged stress. Short bursts of cortisol can sharpen learning, but chronic exposure shrinks dendrites, inhibits the growth of new neurons, and even kills existing ones. This reduces the volume of the hippocampus, weakening the very system responsible for memory and learning. The brain designed to record the past becomes scarred by the very chemicals meant to protect it. The effects are visible on brain scans. People exposed to long-term stress, such as caregivers under relentless burden or individuals in unsafe environments, often show reduced hippocampal size. This reduction correlates with memory problems, difficulty learning new information, and vulnerability to mood disorders. The good news is that the hippocampus retains plasticity. With stress reduction, supportive environments, and interventions such as exercise and therapy, regrowth can occur. New neurons can be born, dendrites can expand again, and memory can recover. The scars are not permanent if the load is lifted. This fragility demonstrates how memory is entwined with life circumstances. It is not a sealed vault, but a living organ shaped by daily chemistry. Stress management is not only about mental comfort, it is about preserving the very structures that allow us to remember who we are. 73. People remember unfinished tasks better than completed ones. The Zeigarnik effect shows that incomplete tasks linger in memory longer than finished ones. When a goal remains open, the brain keeps it active, creating a sense of tension that fuels recall. Once the task is completed, the tension relaxes and the memory often fades. This effect is visible in waiters who can recall large orders before the bill is paid but forget them shortly afterward. This persistence of incomplete tasks can be harnessed productively. Writers who stop in the middle of a sentence often return the next day with ease, because the unfinished state keeps the memory alive. Students who break studying into incomplete segments may recall better than those who cram to completion. The brain resists leaving gaps, so it revisits them. Yet the same mechanism can become a burden. Unfinished emotional business, unresolved conflicts, or abandoned projects may intrude into thoughts repeatedly. They feel harder to dismiss because the mind is trying to tie them off. Rumination thrives on incompletion. The effect teaches that closure matters. Ending tasks deliberately, even with symbolic rituals, can release memory from its loop. At the same time, leaving small strategic gaps can aid learning. The nervous system craves completion, and we can guide it toward productivity rather than obsession. 74. Childhood bilingualism delays dementia symptoms. Growing up with two languages does more than create cultural flexibility. It shapes the architecture of the brain in ways that endure into old age. Bilingual individuals often show later onset of dementia symptoms compared to monolingual peers, even when disease pathology is present. The lifelong practice of switching between linguistic systems strengthens executive control networks and builds cognitive reserve. This cognitive reserve acts as a buffer. When neurodegeneration begins, bilingual brains can compensate by using alternative pathways. Memory decline still occurs, but the symptoms appear later, giving more years of functional independence. The benefit is not magical but structural, the result of decades of demanding neural exercise. The effect is strongest when both languages are used regularly. Dormant bilingualism offers less protection, while active bilingualism forces the brain to maintain flexibility. This continuous practice is like keeping muscles toned. It prevents atrophy and maintains readiness. The lesson is clear. Complexity preserves resilience. By challenging the brain with more than one code, childhood bilingualism sculpts a nervous system that can resist decline longer. Memory is not only protected by biology, but by the richness of experience. 75. Your brain erases and rewrites memories while you dream. Dreaming is not random imagery. During rapid eye movement sleep, the brain replays fragments of experience, weaving them into bizarre narratives. In the process, it weakens some connections and strengthens others. Useless details are stripped away, and essential elements are reinforced. Dreams are memory editing sessions disguised as stories. This rewriting explains why dreams often borrow from recent events but distort them. The brain is testing associations, checking how new information fits with old schemas. The narrative strangeness is a side effect of integration, like an editor rearranging paragraphs. The brain shuffles pieces until they find a place. The erasure is as important as the reinforcement. Without it, memories would pile up uncontrollably, leaving the brain cluttered. Dreams help prune redundant or irrelevant traces, freeing space for flexibility. By morning, what remains is more streamlined, less noisy. Dreams therefore serve dual purposes. to protect the important and to discard the trivial. We awaken not with every detail preserved, but with a refined version of yesterday, lighter and better prepared for today. 76. The prefrontal cortex acts like the librarian of memory retrieval. The prefrontal cortex does not store memories itself, but organizes how they are accessed. It acts as a librarian, deciding which trace to call up, suppressing irrelevant ones, and guiding recall toward the goal at hand. Without it, memory retrieval becomes chaotic, with fragments emerging out of order or at the wrong time. Damage to this region often leads to confabulation, where irrelevant or invented details intrude. The hippocampus may still hold the information, but the librarian is missing, so the wrong book is pulled off the shelf. In healthy individuals, the prefrontal cortex constantly manages interference, allowing smooth recall of relevant episodes. This executive role makes memory flexible. You can retrieve not only facts, but also organize them into coherent arguments or narratives. The prefrontal cortex links memories across categories, guiding reasoning and planning. It is the conductor of recall, turning fragments into symphonies of thought. The importance of this control is visible in aging, where prefrontal decline often leads to difficulties in retrieval, even when memories remain stored. The librarian grows slower, and the shelves feel harder to navigate. Protecting frontal health through mental engagement helps maintain not just memory, but coherence. 77. Music can restore speech in people who have lost it. In cases of stroke or brain injury, individuals may lose the ability to speak while retaining the ability to sing. Melodic intonation therapy takes advantage of this dissociation, using musical phrases to bypass damaged language circuits. Over time, the rhythmic and melodic scaffolding helps rebuild pathways that allow speech to return. This works because music engages bilateral networks across the brain, not only the left hemisphere areas typically responsible for language. Melody and rhythm recruit right hemisphere regions, which can compensate when left-sided areas are damaged. Singing opens doors that speaking alone cannot. The therapy also benefits from the emotional power of music. Patients are more motivated when singing familiar songs, and the reward circuits engaged by music increase neuroplasticity. The combination of structural detour and emotional engagement makes recovery more likely. Music's ability to restore speech reminds us that memory and expression are distributed. Even when one route is blocked, others may be available. The brain is a network of possibilities, and music is one of its most versatile keys. 78. Smiling changes brain chemistry, reinforcing positive memory. The act of smiling, even when artificial, activates facial feedback signals that alter neurotransmitter levels. Dopamine, serotonin, and endorphins rise, creating a state more conducive to learning and recall. When positive mood is present during encoding, memories become stronger because the hippocampus is bathed in chemicals that enhance plasticity. This phenomenon explains why joyful experiences are often more vividly remembered. The emotion is not only felt but written into the biology of the trace. The smile itself acts as part of the context, linking the event to a positive state that later aids recall. In social contexts, shared smiles amplify this effect. Interactions that include genuine smiling are more likely to be remembered warmly and more likely to be recalled during the future decisions about trust. The chemistry of smiling makes relationships memorable. This link between expression and memory shows that small behaviors can tilt cognitive outcomes. The nervous system listens to the muscles of the face and adjusts its chemistry accordingly. To smile is to tell the brain to remember. 79. Memory links to the immune system more than once imagined. Recent discoveries show that immune molecules such as cytokines and complement proteins play direct roles in shaping synaptic plasticity. Microglia, the immune cells of the brain, prune synapses based on these molecular signals, deciding which connections to preserve. Immune activity is therefore not only defense, but sculpting of memory networks. Inflammation disrupts this balance. When the immune system is overactive, it can prune too aggressively or flood the brain with chemicals that impair plasticity. This is why chronic illness or infection often comes with memory problems. The immune system's balance directly influences cognitive clarity. The interaction is two-way. Stress and memory activity themselves influence immune function, altering responses to pathogens. The brain and immune system are entwined in constant dialogue. Memories of stress can even prime immune responses in the future, blurring the line between mental and physical. Recognizing this link expands the meaning of memory. It is not simply a mental act but a bodily one, shaped by the state of defense and repair. To care for immunity is to care for recall, because they are parts of the same network. 80. Trauma survivors sometimes experience time freezing. During overwhelming events, perception of time can stretch or stop. Victims often describe moments of danger as lasting far longer than they actually did, with details etched in slow motion. This is because stress hormones heighten attention and flood the hippocampus and amygdala with signals to mark every fragment. The clock of the brain does not match the clock of the outside world. This time distortion makes traumatic memories unusually vivid. Each second feels expanded, leaving a dense record. Yet the very intensity can fragment the memory, making it difficult to place in chronological order. Survivors may recall sensory details with painful clarity, but struggle to narrate the event coherently. The freezing of time is adaptive in the moment, giving the organism heightened awareness and reaction ability. But afterward it becomes a burden, because the memory refuses to fade as normal experiences do. The frozen scene replays with the same intensity, intruding into daily life. Therapeutic approaches aim to reframe these frozen memories, anchoring them in narrative and restoring flow to the sense of time. The goal is not erasure but transformation, allowing the memory to remain without dominating. Trauma shows how memory can bend time, creating eternity in a single moment. In the end, the human brain is not just an organ of thought, but a living archive of existence, shaping who we are through what we keep and what we let go. Every smile, every scent, every dream leaves its quiet imprint, weaving together the story of a life that is never fixed, but always unfolding. To rest is not to lose time, but to give the mind space to repair, to prune, and to write anew. As you drift into sleep tonight, remember that your brain continues its hidden work, turning today into memory, shaping tomorrow before it arrives, and carrying you gently through the vast landscapes of time and self. If you enjoyed this journey, don't forget to like the video, comment, and subscribe to our channel. With your support, we can make this community of science and discovery even bigger. Share your ideas with us, because it's always more exciting to explore the unknown together. As Carl Sagan said, reality may be much stranger than we realize. Science is the most powerful way to understand this strangeness.